Okay, so we'll now move on to the next talk, which will be presented by Luis Cabrales and Sumita Sarma, and they're going to be talking about electrochemical oxidation of organic compounds in water. Luis.
Hello, everyone. I'm sharing my slides. Okay, so I hope you're doing well this afternoon. So I'm going to be talking about electrochemical oxidation of organic compound in water. So I'm in the Department of Physics and Engineering. And my colleague Sumita Sarma, she's in the Department of Management and Marketing. And we are working on in this project together in produced water. So I'm working on the engineering side. She's working from the side of the business. So let me just start talking about a little bit about produced water. So produced water, as you know, is a byproduct of oil production. For every barrel of oil, around 7 to 10 barrels of produced water is obtained. So there is a lot of produced water around. Some of it is almost like fresh water, so it doesn't have many inorganics other than oil, but some of it has a lot of inorganic components like salts or heavy metals, and some of it is even, it has more salt than the seawater, so some of it can be very salty. So besides oil and salt, it can have some boron and other inorganic materials and heavy metals and such. So what do they do with the produced water? So if they don't have a way to dispose this water, they don't have oil production. So as I say, it's a very large volume of water. So usually there are three ways that they dispose it. So one of them is the underground injection into dispose as well, as the last presentation was referring to. Then also they may use it for enhanced oil recovery, or so steam injection, for example. They may treat it, or sometimes they need to remove some harness or some components from the water, and then they can produce steam. And the other one is for irrigation. So the oil companies, they give the water to water districts, and then they have some, they distribute it to the farmers. So usually how the water is cleaned for irrigation. So for irrigation is a very simple process. So you obtain it from the oil field. Then there is a process where you separate most of the oil. So there are different equipment to remove the most of the oil. So it could be by gravity, it could be by air flotation. And then once the majority of the oil has been removed, then the water goes to another step. Usually they use walnut shell filters. So the oil sticks to the walnut shell, and that way they remove almost all the oil from the water. Once the water is at this stage, then the water goes to the water districts, to the canals, something like that, and then from there it goes gets distributed to the farmer. So that's the usual way they do it. If they need a steam generation, then they may remove the harness or the calcium for to produce steam. Or if the water is too salty, so besides having oil, if once they remove the oil, if the water is still too salty to be used for irrigation or for other purposes, they may need to do other processes. A common one is reverse osmosis, but this process involves high pressure, so equipment is expensive, and to operate that equipment is expensive as well. So what I'm going to talk about is about a particular process to remove the oil from the water. And what we are going to do is do electrochemical oxidation. So the process is quite simple. So electrochemical reaction, you only use electric current and you apply it to some electrodes that are submerged in the water. Depending on what material you use for the electrodes, you can have different reactions on the water. So for example, for produced water, it's common to use some aluminum electrodes, and then the aluminum goes into the water, And these aluminum ions, what they do is that they coagulate the oil particles, so it glues them together, and that way they can either flow them or sink them, depending what how they want to remove the oil. So that's one of the typical processes they do, but we can do different type of metals on for the electrode. So iron, it could be. In our studies, what we use is called mixed metal oxide. So basically it's a titanium substrate, a titanium alloy substrate, and it's usually coated with rare metals, iridium, ruthenium, platinum. And by using these particular electrodes, what we obtain is we generate very reactive species, so hydroxyl, active chlorine, and we also, of course, do hydrolysis. We do produce hydrogen and oxygen. So there are different configurations that we have worked in other projects and in the past, with some of them with collaboration with industry. So depending on the purpose of the treatment, we use many different type of configurations. So we have concentric tubes. So the anode and the cathode are actually concentric tubes, and the electrochemical reactions happens between the gap of the metals. We have used before a fluidized bed reactor, which it has a little bit better efficiency because it has a higher surface, contact surface. And then what we are trying to do now is a multi-cell configuration. This is the project we are working on. And in this multi-cell configuration, we have different layers of anode and cathode. So we have the MMO, and then we have a stainless steel cathode. And so we have 7 different of them. And as you can see, there is a mesh. So the mass transfer in this particular reactor is quite high. We tested it you can see in the picture, we tested it in a batch process, but actually this type of configuration, we could use it as a continuous process, and it could, due to the high surface area, it could have a very good reaction. So what we do is first we test it with a blue dye, because we can control the concentration very well of this blue dye, and we use it to fine tune the characteristics of the reactor. So as you can see, as we increase the amperage, the reaction is faster. So we destroy this blue dye much faster as the amperage increase up to a certain level. So beyond 4 amps, the efficiency, the gaining efficiency is not that great. So once we have this type of data that the students, actually the students got all this data, we analyze it, and we do a simple analysis in order to measure the efficiency of each setup. So that's what we do. And then once we have our instrument parameters set up to be the most efficient, we try to test it in produced water. So for produced water, sometimes it's variable. So depending on where you obtain it, it depends how much oil you are going to obtain. So in this particular case, we measure the oil by something called chemical oxygen demand. So COD, that's what we call. So that this basically is equivalent to the amount of oil roughly. And as we can see, as the time of the treatment increases, our COD decreases until we don't have a non-detectable level. So our reactor is quite good to remove the produced water. So now in the next slide, my colleague Sumita will start talking about her part of the project.
Thank you, Luis, and I hope you can hear me. And hello to everyone. So I'm Sumita Sarma, Assistant Professor of Management. And what I did in this research is, to look into the key questions as to what are the key barriers to widespread adoption of produced water for irrigation of crops, given that Kern County's major industries are oil and gas and agriculture, and what we could do to overcome those barriers. Next slide, please. And this is something, of course, that Luis has already touched upon. Exactly why do we care about this question at all? And the thing is that if we could treat this produced water and sell at a reasonable price, when I talked to the people, it was like around $800 per acre foot, then there could be a lot of potential savings. And given the mega drought that we are facing right now, I think there is a huge potential in the ag industry to use alternate sources of or unconventional sources of water, and oil field produced water is certainly one of them. Next slide, please. Okay, so what I have done here basically in the first phase, along with two of my students, Brandon and Ariel, we conducted around 26 semi-structured interviews, and it was all through Zoom because we went into the pandemic right after we got the grant from Chevron, and thanks to them. We conducted interviews with the 5 major stakeholder groups in this oil field produced water ecosystem. So these 5 stakeholder groups were mainly oil and gas managers and business owners, ag industry experts and farmers, entrepreneurs, water district managers and water board personnel, and environmentalists. So here, I mean, I should have given a diagram, I know, showing the main themes that came out of the analysis of these interviews. But, you know, these are some of the major insights that were revealed. First, definitely the high cost of water treatment, resulting in not being able to provide the final product that is, you know, treated produced water at a reasonable price to the food producers. Lack of one-stop shop for treatment technologies, lack of funding, lack of commercial interest in water management. And as of now, there is no known penalty for re-injecting the water back to the ground. And despite, you know, so many scientific studies, still, you know, effects of reclaimed produced water constituents on agriculture and human health continue to be unknown. So the people, you know, all kind of agree definitely on the acute water shortage and that alternate water streams are required, but they also felt that there should be a tighter collaboration with trust and transparency, most likely along the lines of public-private partnerships. Next slide, please. Okay, and in the second phase, what I did was I developed 2 surveys. And the first survey was a needs assessment survey to the farmers. And out of the 21 responses that I got, 1 farmer only has been using produced water, but then a major portion of them really wanted to use produced water and felt that it could be important. The second survey was kind of like a public opinion where I administered it to the people in and around Bakersfield. Next slide, please. So this is kind of like the snapshot showing the demographics and also some of the behavioral attributes of the people. I'm sorry you're not being able to see the whole slide here, but you know, it's basically what kind of water they like to take. Is it like, you know, tap water? Is it bottled water? And what are some of their other attributes? Like, have they heard of produced water? Do they prefer local food? And so on and so forth. Next slide. Now, coming to the main concerns, what I found was that, you know, younger people, 18 to 29 years of age, are more concerned compared to the older ones. And again, males are less concerned than the females. And the more educated people are, more is their concern about using produced water. Next slide, please. Okay, so this graph shows consumers' preferences for different kinds of reclaimed waters, including oil field produced water. So consumers rated this on a Likert scale. So 1 is dislike and 5 is like. So as you could see, people really prefer rainwater followed by stormwater for irrigation. And interestingly, they actually scored oil field produced water above industrial water and black water for irrigation of crops. This graph shows the different beneficial uses that produced water could be put to. And here, people kind of really showed interest in using produced water more for like external use, you know, like for cleaning or maybe even, you know, watering their lawns, even irrigating crops, rather than using it for more like a direct consumption, such as cooking or even bathing and laundry, which is again, you know, very close to the skin. So people were not very confident about that. And in fact, it showed 90% less preference in using produced water for cooking compared to using it for irrigation. So in sum, what we have found, and also, earlier research has also kind of established, is the OPW reuse is mainly driven by the cost. So when oil and gas companies are making decisions about investing in water reuse and recycling, they are thinking about so many of these different things. But then given, some of the new regulations and the dwindling freshwater supplies, again, more companies are focusing on this produced water reuse. So the finding has been that there is certainly immediate need for design testing and commercialization of suitable cost-effective technology to treat this water, and so that we could provide this water at a reasonable rate to the farmers. Next slide, please. And then in terms of infrastructure, I think transporting produced water to a large central facility could be very, very cost intensive. Plus also there could be, problems of corrosion and so forth. So a modular distributed network of water treatment plants could be one way out, as long as this could be supplemented by, a product recovery plant, as in critical materials extraction or raw earth extraction. So that way, it could be providing a more valuable value proposition because, while talking to two of the entrepreneurs who are actually engaged in this critical material extraction, what they said is that the demand for critical materials is increasing, and the high-tech industry is relying on increased imports to meet this demand. So we would want to produce this more in-house within the United States. And then last but not the least, we need to be very careful about media sensationalism and how to avoid that. And so that we could mitigate the public's, disgust of direct or indirect consumption of produced water, as well as their distrust of oil and gas companies in general. Thank you so much. Any questions?
Thank you. We have time for one question, and John Yu has his hand up. Go ahead, John.
Okay. Yeah, I have a question, Louis. And that's a good research work, but I want to make sure. Have you guys done any field tests, field application in the real?
For what?
Hmm?
For what? Could you repeat the question, please?
The fuel application.
Fuel?
The actual. Now you guys done experimental work in the lab. But
yes, right.
Actually, do you actually apply to the field, or just
yes,
do the prototype? But
for this particular design, it has been all lab work. For a different same principle, for a different design and a different setup, I use it for a different project in the field to clean water.
Okay.
It was a different setup, and but the principle is the same.
Okay, I understand that. Yeah, but this is just my comment because I worked in a regulatory agency before. Any produced fuel water you cannot apply to the service in any way. Is against the regulations. You have to clean up. You have to pure. Yeah, you can't directly use those water. Yeah, even some of the water, I know some of the field, the water is relatively clean, and but you still cannot use it. You still cannot dump it to the service.
Yeah, we have used produced water, we clean it and things like that, and they irrigate in the field. Actually, we work with a oil producer who also has his land, and he irrigates his land. He has his process to treat the water, and we since he already has all this, because the permit was an issue in that particular project, to find another place where we could get a permit to irrigate with produced water was complicated. So we had to do it with this particular oil producer. who already was irrigating. He was treating the water one way, and we were doing a different way.
Oh, okay. 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 Good. Thank you.
Thank you.
Yeah, I just want to clear with this. Okay. Thank you so much.
Thank you.
Thank you very much, Luis and Sumita. In the interest of time, we need to move on. So if there's other questions, please write them in the chat, and Luis and Sumita will attempt to answer them.